So we were discussing related to goodness of fit of the model, means how the model is fitting the data, that is related to model diagnostic. In the first part, we discussed the model estimation that consists of likelihood value, omnibus test, that is a form of likelihood ratio test, and the pseudo R square. And the second thing is related to the real prediction part, where we compare observed values and the expected values from the model. And in that part, we have already discussed the Hosmer-Lomachenko test. Now, I'm introducing a new concept that is related to predictive accuracy part. Right? So, as remember, we have discussed this part, that is the Hosmer-Lomachenko test. That is the direct comparison of observed frequencies and the expected frequency. Uh, Nearer the values are, the smaller the difference, means the model is a good fit. Here, I'm introducing a matrix that directly compares observed value and the estimated value. Right? So for that, let me have uh, one more slide. So now here we will be discussing a new concept, that is the classification matrix. Sometimes this is also known as confusion matrix. The objective of this matrix is to comment on goodness of fit, fit of the model through the prediction part. Means directly comparing the observed values that are given and the predicted values or the estimated values from the model. Okay. So for this, let us consider a matrix. Just a moment. On one side, we have observed values, and the other side, we have predicted values. Okay. Suppose here we have observed values. And here we have predicted values. Okay. So in observed value, there can be two values, 0 and 1. And on the other side, we have, right? So one value can be 0, right? And the other value can be 1, right? 0 means no or the negative value. 1 means the positive value. And here also we have 0, that is the negative value. The 1 is the positive value. Right? Now, if we look for this value, here the actual value is negative and it has been predicted as negative, right? So this is known as true negative because the prediction is correct. Here, the actual value is the positive value and the predicted value also comes out to be positive. So this is known as true positive value. Now here, actual value is negative, but it has been predicted as positive. So this is known as false positive because it has been predicted as positive, but it is a false prediction. Here, It has been predicted as negative because this is 0, but actually this is a positive value. So this is known as false negative, right? So this is the matrix that we discuss here. So here it is there. Here we have observed value. Here we have 0 or the negative values means not happening. 1 or the positive value means happening. And related to the predicted part, here 0 is the negative which is not happening and 1 is the positive that is happening. This is true negative, which is the correct prediction. This is true positive, which is the correct prediction. Here, as I have mentioned earlier also, it has been predicted as positive, but actually it is a negative. So this is false positive. Here it has been predicted as negative, but actually it is positive. So this is false negative. Okay, right? So this, on the basis of this, we develop a classification matrix. Now, before starting that, how it is being done? It is decision on the base of cutoff probability. Normally, the default cutoff probability is 0.5. The values greater than 0.5, if we have the probability value greater than 0.5, they are put in the positive box or the 1. And if the values are less than 0.5, that is being put as the negative. Okay. So as we see here, true negative and true positive are the correct prediction. Right? So their percentage is known as hit ratio, which is the overall accuracy. That is a percentage of correct prediction. So they would be true negative plus true positive and sum of all. That is true negative plus false positive plus false negative plus true positive, right? So this is the correct prediction that we have. Okay. But no, let me show you this value, then I will be coming back on this. So as you see here, this is the classification table. Okay. And if we look for the values, this is correct prediction. Okay. This is also a correct prediction. So if we sum them, means sum 75 plus 105, right? These are the correct prediction. Total number of values are 200. So that would be 180 upon 200. So 90% is the correct prediction. Okay. So this is a hit ratio, means model is able to correctly predict 90% of the observation, means 90 out of 100 observations are being correctly predicted, right? So this model appears to be good, but there is an accuracy paradox also with this type of value. Let me introduce this accuracy paradox. Okay. Now here, let us take two examples. Now we are discussing accuracy paradox. Suppose we are we are predicting um, whether a person is the main objective is to predict the loan defaulter. Hmm. We have two category, that is zero. Zero means loan worthy, not a loan defaulter. And the other one is one, that is the loan defaulter. We have equal number of cases in both these two categories. Suppose here the not loan defaulter is 100% correct prediction. Okay. And here we will be have a prediction of just 50%. That is the correct prediction. Okay. And if we go with the overall percentage, so 75% is the overall accuracy. So we say, if we look at the 75% value, means 75% is the correct prediction, it looks to be a big value. It looks to be a good value, right? That our model is able to predict the loan default or not the thing 75%. But actually, as we see here, our main concern is related to identifying the people who are possibly the loan defaulter. And here, the actual accuracy is just the 50%, right? So this is not a good measure. Is that okay? In this case, this is not a good measure. In the same way, suppose we have some unbalanced data, like um, mm, some financial frauds. Now, we have only two categories. One is the fraud and other is normal transaction, non-fraud. Okay. We have just 5% observation in the fraud and 95% observations in non-fraud, which is obvious, right? Now, we don't run any model. We simply say that if we put, if we put everyone, every transaction into non-fraud part, right, then our model would be 95% correct, right? Because this is an unbalanced data. So if we put all the observation without any classification into the non-fraud part, then also our model would be 95% correct. Is that okay? So overall accuracy here is 95%, but there is no effort to identifying fraud. So again, this is a misnomer, right? So this concept is known as um, this concept is known as accuracy paradox. Okay, this is known as accuracy paradox. That model with higher overall accuracy, its ratio might not be a better model, right? Higher accuracy for predicting a relevant class is more important, right? So we have other measures also like sensitivity or recall, that is known as ability of the model to correctly classify or predict the positive value, that is known as true positive value. Okay, just a moment. Okay, so here let us discuss these measures also, right? Like the measure that we are discussing is related to the recall or sensitivity. It is the ability of the model to correctly classify the positive values. Okay, right? That is a true positive rate. So this is the ratio of true positive divided by true positive plus false negative, right? So the true positive case here is 105. Okay? This is a true positive, and the other one is 105 plus 10, that is 115. So again, this is a big value, right? Right. The next one is the specificity, ability of the model to correctly classify the negative. Opposite to this is a true negative case. So this is true negative. True negative is 75 and divided by the total of that case, that is a true negative plus false positive, that is 75 plus 10, that is 85. This is 75 divided by 2. Again, a big value, right? But if now, as we see these two values, there is not much of the difference. So there is no need for the trade-off, right? Both values are equal. But sometimes sensitivity may be high and specificity would be low. Means true positive rate would be high and true negative rate would be low. And in some situation, this is opposite case, that specificity would be high and sensitivity would be low. So in that case, we have to decide which one is more important, right? So So there is always a discussion between that. And accordingly, we have a F ratio also, which is the harmonic mean of sensitivity and the precision that lies in between these two values. Okay. And precision is actually the measure of accuracy of the positive classified by the model. Okay? Let me explain that. This is the true positive divided by true positive plus false positive, means which are predicted as positive. Okay. So here the true positive is 105 and false positive is 105 plus 10. So again, this is 105 upon 115. This precision is a high value here. Okay. But if there is a big gap between sensitivity, that is this value, and the precision, we use F ratio, right? F score, which is the harmonic mean. As we check the formula, this is 2 times sensitivity into the precision divided by sensitivity plus precision. Right? This is the harmonic. But here, since there is not much of the difference, there is nothing to be bothered. So it is irrespective of the fact whether we use overall accuracy or we use sensitivity, specificity, precision, or F score. All gives us the same values, right? Okay. So this is related to the model accuracy part. Right? And here, as we examine, the overall model is doing good. Now, we come to the next part that is related to testing significance of the coefficient. Since a number of coefficients are there, so we examine whether these coefficients are significant or not. Remember, in the case of the regression analysis, we examine H naught, we examine significance of the beta coefficient. Okay, but here, instead of the beta coefficient, we consider the Wald's coefficient or the Wald statistic. So Wald statistic is simply the square of the ratio of beta coefficient and standard error of the beta coefficient and the square. Okay, right? So this is the objective, testing significance of the coefficient to examine whether the logic is zero or not. Right? Means whether that predictor is significant or not, with the hypothesis as that predictor is insignificant. Since predictor is insignificant means the P would be, this is the case that I have introduced earlier also, right? This is the case. If that predictor is insignificant, then probability of classification would be exactly 0.5. So odd ratio 1, 1, and logic would be 0. Means it cannot predict whether the things would go in the positive class or things will go in the negative class. Right? Okay. So this is the thing that we discuss, whether an individual independent variable is insignificant or not. Right? So if that is the case, so if that is significant, then probability would be 0.5. If probability is 0.5, then the odds ratio would be 1 and the log of odd would be 0, right? And if this is not the case, then either it goes to the positive thing or goes to the negative thing. This is being written. So here we examine the Watt's coefficient. This is the formula. And if the p-value is less than 0.5, 0.05, so we reject H naught, and accordingly we say that predictor is significant. Okay, so let us discuss the results first. Right. So as this is a Wald coefficient that I have discussed, and here we consider the significance. This p-value is 0.003, so this value is less than 0.05. So departmental identity is significant. Improved visual is not significant. Youthfulness, the p-value is 0.000, which is less than 0.05. So youthfulness is significant. Then emotional connect. Okay. This is also significant, right? So these three predictors are significant, right? And other predictors are not significant. Yes, constant is significant, that's okay. So three predictors, that is a departmental identity, youthfulness, and emotional connect, all showing low p-value. So H naught is being rejected, means Ward coefficient is not zero. So these are the significant predictors, that is the model accuracy, usefulness, and emotional connect. Okay. So let us write the significant predictors on our whiteboard. So here, as we have examined, the significant predictors are, we write the result here. The significant predictors are, the first one that was written here is departmental identity, means the logo should reflect the departmental identity, means it should look the logo of a police department, of a law enforcement agency. The second thing is it should give the image of youthfulness. The logo or the rebranded thing should look um, uh, a youthful thing, a vibrant thing. Right? And the next one is it, since this is related to a law enforcement agency which provides us a feeling of security, so there should be an emotional connect with that, right? So these three are the significant predictors, right? So here we have discussed the significant predictors. Now we consider the directionality of the relationship, right? As um, remember in the model that we have introduced, remember the model in the start, right? And this is the log of odd ratio, which is equals to the z, that is equals to beta 0 plus beta 1 x1 plus beta 2 x2 goes up to beta 6 x6. So here betas are directly connected to these log values. So if we interpret these betas, just like the regression coefficient, we are interpreting the logic only, right? Which may not give the meaningful thing. But if we take the anti-log of beta, right, then that becomes anti-log of logic, that becomes anti-log of logic, right? Means that becomes equivalent to odd ratio. That is easier to be interpreted. Is that okay? So here, instead of interpreting beta, we interpret the exponented beta, which is the anti-log of the beta. Right? Okay. Right? As it has been mentioned, that this beta, since it is related to the logit, that was log of p divided by 1 minus p. So this is known as logistic coefficient, which is not interpretable in that form. So we consider the exponented coefficient. These are the exponented coefficient, which is the anti-log of the beta, which is connected to the odds. Okay. And remember, if logit is positive, it means the positive chain. If logit is negative, that is the negative chain. So if logit is positive, means exponented coefficient would be greater than 1. We have positive relationship. If logit is negative, then we have exponented coefficient less than 1. That is the negative relationship. Okay, right? So we examine whether the exponented coefficient is more than 1 or less than 1. Right? So let me show you the results so that we have a better connect. Right? So this is the exponented coefficients. Right? So though if we consider these things like improved visual, sorry, departmental identity, this is more than 1, youthfulness more than 1, emotional connect more than one. So all three are having positive relationship because here the exponentiated coefficient are more than one, right? They are positive relationship. But if we connect, if though superficial is not significant, so it is no point of interpreting that. But in case superficial was insignificant, right? So here the exponentiated coefficient is less than one. So it has a negative relationship. Means as the superficialness increases, there will be uh, tendency of moving towards the zero part, tendency of moving towards the non-like part, dislike part, right? So here we have the negative relationship. But since it is not significant, so we are not discussing them. Okay. So this is the interpretation of that. After that, we consider the magnitude of the relationship, means which one is at the top of the hierarchy of the significant predictor. So here also we will be interpreting the exponentiated coefficient as we discuss on the PPT. Right? So here we interpret the magnitude of the relationship. Again, we will be interpreting the exponentiated coefficient. It reflects the magnitude change in the odds. Okay, so percentage change in the odds is exponentiated coefficient minus 1 into the 100%. Okay, so I'm showing you the value. Then after that, I'm writing down the value. So to make an interpretation. Here, the departmental identity is having an exponential coefficient of 5.7691. Youthfulness is having an exponential coefficient of 5.859. And the third one, emotional connect, is 4.69. Here, the highest exponentiated value is youthfulness. So the youthfulness is the predictor that affect with liking and disliking of the logo majorly, followed by departmental identity. And at the third place, we have emotional connect. So let me write the values. So here we will be writing, just a moment. We are writing the exponential coefficient. The departmental identity is having 5.769 exponential coefficient. Youthfulness very nearby. This is 5.859. So there is not much difference between these two values. So we can take both as the number one, 4.65. So if we compare these values exactly, so this is the most important predictor in affecting likeliness and dislikeliness. This is at the number two, departmental identity, and this is the number three. Okay. But these two values are not much different. But now if we make the interpretation as we have mentioned here, right? So percentage change in odds by youthfulness. That is 5.859 minus 1. This is 4.859 into 100%. Means 485.9%. It means if we change the youthfulness by 1 unit, there will be a change in the odds in the same direction by 4859. Means if we increase the youthfulness by 1 unit, the percentage change in the odds in favor of likeliness would be increased by 485.9. Okay. So this is the interpretation. Now you can interpret the other values also, right? So this is the interpretation. In the end, we have validation of the result. So for that, we divide our sample into into two subsample. One is the training set where we develop the model, and on the other set, we check whether the model is valid or not. That is the holdout sample case. Hmm. These are the SPSS window screenshot that gives you how you can run the model using that. Okay. So this is approximately all about the logistic regression model. Just to show you the probability part, that because we have saved just to demonstrate, we have saved these two variables also, that is the predicted value, predicted probability, and the group membership. Here we use the cutoff value as 0 0.5. So you can check if the probability is greater than or equals to 0 0.5, it has been predicted as 1, means yes, like. And if the probability of occurrence is less than 0 0.5, it has been predicted as 0 or no. You can check. The first value is 0.99, that is greater than 0 0.5, greater than or equals to 0 0.5, so 1. Right? The next value is less than 0 0.50. Next value is again less than 0.50. Next value is again less than 0 0.5, again 0. Right? Like here, this value is greater than 0.5, 0.7103, case number 13, and it has been predicted as 1. Okay, right. So this is the model. So here, by this model, we predict whether a unit can be classified as one of the category of two. So it is a very useful technique classification. In many situations, we have the dependent variable as as the categorical variable. So in that case, we have to use a classification technique, like in this case. So here, what would be our suggestions to the police department? That in order to increase, though we suggest that there are three predictors that may affect the rebranding success of the rebranded logo, that is departmental identity, youthfulness, and emotional connect. And among these three, youthfulness is at the top, closely followed by departmental identity and emotional connect. So if we want to really improve the rebranding part, they have to take care of these features. Okay, so this is all about logistic regression. Thank you.